This is the lecture that goes along with section 6.1 from our calculus book. We're introducing some new ideas here. The first and foremost is that we're going to be talking about differential equations. Simply put, a differential equation is an equation, meaning it has an equal sign, and has a differential. dy is a differential. dx is a differential. Those are the elements that we use to build our derivatives. So maybe we could just think of a differential equation as an equation with a derivative. Um, the order of a differential equation has to do with how large the derivative is. And the problems that we're going to be doing today, all of them are first derivatives. So these are all considered first order differential equations. The act of solving a differential equation is called anti-differentiation. So for example, if we focus on the very first problem, what is the solution or find the functions that satisfy this differential equation? Well, we could say, let's undo the derivative and say, well, what function has a derivative that's secant squared? Well, that's tangent. What function has a derivative which is 2x? Well, that's x squared. What function has a derivative that's 5? Well, it's 5x. And then let's put a plus c at the end of it to say we have the most general antiderivative. They've got all the functions that fit this particular differential equation. Now we can always check our answer. We can check our answer by taking the derivative of our solution, and I take the derivative of tangent, and I get secant squared. I take the derivative of x squared, and I get 2x. I take the derivative of 5x, and I get 5. I take the derivative of c, and I get 0. And we can see that this, 0, that is a perfect match for where we started. So that's a solution. All right. Now, this is referred to as a general solution because it meets, sorry, that's not the general solution. The general solution is right here, okay? Meaning that it fits all the possible situations for that differential equation. Now, we can also find a particular solution, and in a particular solution, we find a general solution and then have it meet some criteria. In this case, we're going to meet the criteria that the solution has to go through the point 1, 0. Let's start with our differential equation, dy dx is equal to e to the x minus 6x squared. And I want to find the antiderivative of that. So that's y equals a function whose derivative is e to the x. Oh, that's e to the x. A function whose derivative is negative 6x squared. That's a little harder. But we're going to introduce something idea called the inverse power rule. Sorry, the anti-differentiation power rule. I'm going to set the negative 6 side. I know that when I take a derivative, I make the exponent one smaller. When I take the antiderivative, I make the exponent one bigger. And I'm going to end up multiplying by the reciprocal of that exponent. Okay, and I think I've done this correctly. Y equals e to the x. 6 times 1/3 is 2x cubed plus c. Now, again, we can always test our answer by taking its derivative. Derivative of e to the x minus 2x cubed plus c is e to the x. Bring the power down, that's negative 6. Reduce the power by 1, and then plus 0. And we can see that, indeed, that matches our original differential equation. So that's, again, this answer right here is a general solution. But if we want to make sure that it meets a particular criteria, we can go to our general solution. Everywhere we see a y, put in a 0. Everywhere we see an x, put in a 1. And then we can solve for c. 0 is equal to e minus 2 plus c. Let's subtract e from both sides. Let's add 2 to both sides. And I get 2 minus e is equal to c, which means our particular solution is y equals e to the x minus 2x cubed plus 2 minus e. And again, this is our particular solution in that it solves the differential equation, and it also meets that other criteria. It goes through that point. Let's try that again. Find the particular solution for this differential equation, and its graph goes to 0, 3. Oh, and mind the discontinuity. Let's talk about that in a little bit here. So let's start with that dy dx equals 2x minus secant squared x. Y would have to be, well, what function has a derivative that's 2x? Well, that'd be x squared. And then derivative, the antiderivative of secant squared is secant x plus c. And again, just for good measure, we can take the derivative of our proposed solution and see if we go back to our original equation. And it does. It works out. Great. So what about that particular solution? Well, let's take our general solution. Our general solution, every place we see a y, let's replace it with 3. Every place we see an x, let's replace it with 0. And we get 3 is equal to c, which means that our particular solution would end up being y is equal to x squared minus tangent x plus 3. Now, it does say here about minding the discontinuity. Well, it just so happens that this solution is not valid everywhere because this differential equation is has discontinuities at, pi over 2, 3 pi over 2, 5 pi over 2, and all the negative versions of these. So plus or minus, plus or minus, plus or minus. Every place where there's a discontinuity, there's a problem in that differential equations describe how things change. Well, when we hit that discontinuity, we don't know how things were changing at that moment. So we say that this solution is only valid in the area where there's continuity. Because x equals 0 is in the interval from pi over 2, negative pi over 2 to pi over 2, we say that this solution is only valid in that particular interval. Fantastic. All right. Now, problem. What happens if we're asked to find the solution to a differential equation where we don't know the antiderivative? Now, normally I just say, well, the antiderivative of e to the x squared, I don't know, maybe it's e to the x, negative e to the x squared. Maybe I'd say that's what I think the antiderivative is. But we do a quick check, take the derivative of that proposed solution, and we get, let's repeat. Oh, wait, there's a negative 2x. That doesn't match that. And I could work at this a long time and not find the antiderivative of that. That's because this problem is a tricky one. The antiderivative doesn't exist. This is not a solution. There is no antiderivative. So what are we going to do? Well, it says here to remember FTC Part 2. Well, there's a couple different versions of FTC Part 2. The one that we're most familiar with is that the integral from a to b of f of x dx is equal to big F of b minus big F of a, where big F prime is little f, i.e., big F is the antiderivative of little f. That is one version, but the one that we're going to use for this looks like this. F of x is equal to f of a plus the integral from a to x of f prime of t dt. Now let's put this through the ringer and let's see where it ends up. I know f of 7 is equal to 3. So I'm going to write f of 7 plus the integral from a to x of f prime of t dt. So this is equal to f of x plus the integral. Notice the a is here and here from 7 to x of f of t, f prime of t dt. Which means I'm going to change this to e to the negative t squared dt. Or f of x is equal to 3 plus the integral from 7 to x of e to the negative t squared dt. You're like, that doesn't look like a function. And if it is a function, does it really meet the criteria that we set out for? Well, let's try one quick thing. Does f of 7 equal to 3? Does f of 7, which is 3 plus the integral from 7 to 7 of e to the negative t squared dt, well, integral from 7 to 7, that's a rule. That's going to be a big fat 0. It's equal to 3. Oh, so we meet that criteria that it goes to that point. What about the derivative? What happens when I take the derivative of this proposed solution? Well, derivative of 3 is 0. The derivative of the integral from 7 to x. Well, this looks like an application of fundamental theorem of calculus part 1. And we get e to the negative x squared. E to the negative x squared. That's what we said the derivative was. So we meet both criteria. So every function, every function that goes to a particular point, we can use this particular ploy and find a solution, even if we can't find an antiderivative. Now, if we were to go into our calculator and say, is this really graphable? Is this really a function? Well, let's take a quick look at that. Let me get to the calculator. I'm going to go into graphing mode. I'm going to go ahead and type in 3 plus the integral from 7 to x of e to the negative t squared dt. And does this graph? It sure does. We have a function. It's for any individual value x. For any individual value x, we can find a value for that function. In fact, I could go up to 3, go up to 7, and we can really see that, yep, it really does equal to 3. All those kinds of things are true. So this really is a solution to that differential equation. Let's continue on our discussion having to do with differential equations. We now know that sometimes differential equations are not solvable. The antiderivatives don't exist. Let's talk about what we might do if we don't know how to find a solution to a differential equation. We might use a method where we say, you know what, the derivatives represent slopes. And if we put x and y values in, they represent slopes at particular locations. We might say, for a particular differential equation, what is the slope at some location? And we draw a little line representing those slopes. So, like for example, here's a differential equation, dy dx is equal to x plus y. Let's say we find the value of the derivative at 0, 0. Oh, that's 0 plus 0. That's equal to 0. Great. Let's take that information and let's put it on the graph. Let's say right here, there's 0, 0. And then, let me change this to red so it pops a little bit. Let's put in a line with slope 0, a horizontal line. Oh, that was so much fun. Let's do it again. How about, so let's find the slope at point 1, 0. So dy dx at 1, 0. is 1 plus 0, which is equal to 1. So let's go to the location 1 comma 0 over 1 up 0. That's right here. And let me put that 45-degree slope line that we associate with the slope of 1. Okay, let's do it again. This time, let's do it, let's say with dy dx is, we want to know its value at 0 comma 1. 0 plus 1 is equal to 1. 1 again. So let's go here over 0 up 1. Now I'm here and I get 0, 1. You know what I think would happen is if I do this along this line where there's the the x and y values are kind of on this diagonal, let's say like at dy dx, how about negative 1 comma 2, negative 1 comma 2, I get negative 1 plus 2 is another 1. I think along this diagonal, all of these would be the number 1. Now, this is not a trend that's going to be happening always, but it happens on this particular differential equation. And I think we can exploit that pattern and simply put in all these slopes of 1 wherever we're on that diagonal. And come to think of it, I think if we're on the diagonal just below that, let's say at dy, oh no, dy dx, when I'm at 1 comma negative 1, 1 plus negative 1, that's equal to 0. And that means right there I get a 0. I think I've got zeros on this diagonal as well. And even with all of this pattern recognition, this task of finding these slope lines is still really tedious. How about dy dx at 2 comma 0? 2 plus 0 equals 2 over 2 up 0. So here's 2 comma 0, and we're steeper than we were at with a slope of 1. And right here as well, we might find that the value of the slope at, oh, what is that? 0 comma negative 1 is negative 1. So we put in our slope lines there, and it ends up being true for all along those diagonals as well. Oops, a little low there. And we'll do one more. How about dy dx? We'll go one lower than, no, we won't. We'll go to negative 1, negative 1, negative 2. So here we are at negative 2, steeper than the negative 1 lines. And still, again, all of this nifty pattern recognition, I'm getting tired of doing this. So we kind of recognize what we have, got those little lines there, but what good is it? Well, if I ask you, hey, what about a curve that satisfies this differential equation and goes through the point 0, 2? Well, I might plot a point here at 0, 2, and I said, well, what if I had a line that moves consistently with those slope lines? Something like that. The slope, the differential equations provide the slopes and tells me how I'm going to change. This initial condition tells me how I'm going to go. And I can get what was referred to as an estimate to a solution curve. Now, this is pretty fun to do by hand, meaning that it's not fun at all. But one thing that calculators are really good at, calculators are really good at doing things that are tedious. So I'm going to go to our calculator. I'm going to add another graphing page. And I'm going to change the setup for this particular graphing page not to be in function mode. We're going to go into this graph entry edit mode and say not in function mode, but you can see there's an option here. It says differential equations. If I choose that option, it gives me the opportunity to type in the differential equation. Now I can type in the differential equation as x plus y, and if I hit enter, nothing happens because there's something subtle going on here. The differential equation here is in the form of y1 prime, which means my y variable is actually referred to as y1. And if I hit enter, look at that. It's got all of those little lines as if it went through and calculated all those slopes. Let's play around. Let's play around with this particular slope field for a little bit. I'm going to make a copy of it into our notes. Go over here, paste it in. Nice and big. Okay. With the idea here, again, if I would have started here at 2, 0, I could say, hey, look at me moving consistently with the slope lines. Okay. What does it mean to mean consistently with the slope lines? Well, it means that I don't go through them like this. This is like a slope of 0, but this is like a slope of like 10. You know, when I move, I'm moving consistent with those slope lines. And there is a relatively good estimate of what the solution curve would look like. And if I started down here, let's look like if I go this way, I'm going to go down here. And if I move this way, kind of going with the flow, I end up something like that as well. So we can throw in these estimates of these curves. And if we could do this by hand, I bet you the calculator can do it just as well. For example, if I say, again, tab to get up to where I'm editing the differential equation, if I go here, there's a nice little spot here for us to put in a location, like over 2 and up 0. And if I hit enter, boom, there's their estimate as the solution of a slope curve. Okay. And how's that compared to ours? I think ours compares pretty favorably. Pretty favorably. All right. So, a very typical thing that the College Board will ask you to do is to kind of match up differential equations and their slope fields. So, for example, we might look at these 4 slope fields and these 4 differential equations and say which one matches with which. Okay. Now, how might you attack this problem? Well, here's a couple ideas. One, um, all three of these, all three of these have x and y being either multiplied or divided, which means when x and y are both positive, it's going to only produce positive values. And we can see in here and here and here only positive slope values. This one has a combination of positive and negative in the first quadrant where x and y are both positive. And this differential equation is the only one that has the ability to produce negative slope values in the first quadrant. I am going to declare, therefore, that graph B and differential equation A or 1 are matching. Okay. Now, what else could we do? Well, this is interesting. This one has a divide by y. That means whenever y is equal to 0, I should have undefined slope line, something that's nearly straight up and down. That seems to occur right here. Oh, I'm sorry, I got that backwards. That seems to occur here. When y is equal to 0, I've got nearly vertical slope lines. All right. I think 3 and A go together. Okay. The opposite true here. Here, where X is equal to 0, I should see nearly vertical lines. That seems to be happening here. So maybe 4 and C go together. And that leaves 2 and D. Now, what do we see here? Well, when Y is being held constant and I go this way, I see my slope lines getting bigger, just like as X would get bigger. When X is being held constant and Y is getting bigger this way, you see the slope lines again getting more and more vertical, getting larger. Okay, so those look like a good match. So here's my reading of that combination. Okay. As we move away from slope fields, we can talk about, well, we're going to talk about Euler's method. Now, Euler's method, actually, I gave you a little sneak preview of what Euler's method does. When we drew, or when the calculator drew the solution curve, going through that point, each of those dots actually represents Euler's method. It represents the idea that we could um, say, start at some location and say, let's move linearly along the slope line for a little bit of distance and find a new location. Plot that, then move to the next spot. It's a very procedural method that we can use to uh, estimate solutions to differential equations. Let's take a look at this using that differential equation x plus y and the starting point 2 comma 0. We are going to go from uh, x equals 2 to x equals 3. And we're going to do so in 2 jumps. So we're going to go from 2 to 3 in 2 jumps, which means each jump is going to be 1/2 wide. We're going to start at 2, and we're going to get bigger. The delta x is going to get bigger by 1/2. Now, here's how the rest of this method works. We're going to find out the size of the slope at that location. And in this case, the slope is 2 plus 0, which is equal to 2. Now, how much the y moves is dependent on the value of dy dx and multiplying it by the value of delta x, or in this case, equal to 1. Now, these are going to be our new x and y values. We're going to get the new x value by taking the old x and adding the delta x, and we're going to get 2 plus 1/2 is 2.5. And the new y value is going to be the old y value plus the delta y. 0 plus 1 is equal to 1. Great. We've now got an estimate of the location at when x is 2.5. We're going to take that value. We're going to use that as a new starting point, and we're going to do the process again. So still going to move 1/2 over. Our dy dx is 2.5 plus 1, or 3.5. Our delta y is going to be that 3.5 times 1/2, which is 1.75. Our new x value is going to be 2.5 plus 1/2, which is equal to 3. And our new y value is going to be 1 plus 1.75, and that's equal to 2.75. To summarize, we have now just estimated that f of 3 is approximately 2.75. Well, does that match what we saw in that calculator screen? Well, the calculator is doing the step size is being a little bit bigger. I'm going to hit tab, go up arrow, and I'm going to go where our differential equation is being defined into this triple dot called edit parameter. You can see that it is using Euler's method to make its calculations. And if we go down here, you can see that it is using a plot step, which we call delta x of, of 0.1. Let's change this to 0.5 and hit OK. You can see now that the dots are a lot more spaced out. I'm going to go ahead and get trace mode, graph trace, and I'm going to move my right arrow key, and you can see here's where we started at 2 comma 0. And if I move over, there's that 2.5 that we said was an estimate when, sorry, there's where x is 2.5, and it estimated the y value is 1, just like we did. And when x is 3, it estimates the y value at 2.75, just like we did. Now, the closer the points are, the smaller the x step, the better the estimation is going to be. Just like when we were doing estimates using Riemann sums, the more slices we made, the better estimates of the area we get. Same thing goes on here. So if we do more steps, we'll get better estimates. Also, by the way, we moved to the right because our delta x was positive. We could have moved to the left and found estimates that way. All we would have had to do is make our delta x negative. Let's try this again with a different differential equation. See if we can do this table by memory. We've got an x and a y value. In this case, the x value is going to start at 2, and the y value is going to start at 3. It says we want to take 5 equal steps to go from x equals 2 to x equals 1.5. 2 minus 1.5 divided by 5. Oh, I'm sorry, I did that backwards. 1.5 minus 2. So this is negative 0.5 over 5. Looks like we're going to move with a negative 0.1 delta x. We also have to calculate the dy dx. In this case, this is 2x minus y, or in this case, it's going to be 2 times 2 minus 3. 4 minus 3 is 1. Then we can calculate our delta y, which is dy dx times delta x. In this case, dy dx is 1, and delta x is negative 0.1, giving me a negative 0.1 delta y. And then we get our new x value and our new y value. Our new x is going to be 2 minus 0.1, or 1.9. And our new y value is going to be 3 plus negative 0.1, or 2.9. And then we start the process over again. So 1.9, 2.9, still with the negative 0.1. I've got 2 times 1.9 minus 2.9. See, that's 3.8 minus 2.9. That looks to me like 0.9. 0.9 times negative 0.1 is negative 0.09. My new x value is going to be 1.8, and my new y value is going to be 2.9 minus 0.9. I think that's going to be 2.81. And then we do it again. And perhaps at this point, we're starting to feel like this is really tedious. 2 times 1.8 minus 281. And the numbers are getting pretty darn ugly. 2.8 times 2 is 3.6 minus 2.81. Gonna have to borrow one from there. 10 minus 1 is 9. I'm gonna have to borrow one from there. 15 minus 8 is 7. So it looks like we got ourselves 0.79. So 0.79 times negative 0.1 is negative 0.079. This is going to be 1.7. And then this next one is going to be 2.81 minus 0.79. Carry from there, we get a 10. It's a 1. Carry from there, get 10 minus this is 3, 7, 2.731. And already I'm feeling pretty tired of this. So if we talked about the fact that the calculator can do these tedious things easily and quickly, perhaps we can say the same thing is true having to do with other technologies that we might have we might play out for this. And for this particular problem, the right tool is a spreadsheet. So I'm going to go ahead and in a web browser, I'm going to go to sheets.google.com. I'm going to use a Google Sheet. I'll start with a blank spreadsheet. I'll make this 200% so it's easier for you to read. Okay. And I'm going to go ahead and put our headings on here, delta x and dy dx and delta y. And then here's our new x and our new y. All right. We started with this previous problem, starting with x is equal to 2, y is equal to 3, and we set our delta x to negative 0.1. All right. Our dy dx was 2x minus y. Now, one of the powerful things about a spreadsheet is that besides putting text in a cell or a number in a cell, we can put a formula in a cell. Formulas always start with the equal sign, and then we can do cell references. So for example, I want to do 2 times x, but the x value is being stored in this cell A2. I click on it, and the cell A2 appears. Then I can say minus, and I want to subtract the y value, which is being stored in B2. If I click on B2, that cell reference shows up there. If I hit enter, it calculated that one value just like we did by hand. Delta y was the dy dx value multiplied by the delta x value. And there's that negative 0.1. And then I can say, you know what I want to do? I want my new x value. It's going to be the old x value added to the delta x value. There's my 1.9. Equal sign to find the new y value, which is the old y value added to delta y. And that looks like exactly where we ended up when we did this by hand. Let's double check. 1.9, 2.9. Excellent. Now let's go ahead and do the next row. Now I'm not going to type in 1.9 and 2.9. I'm simply going to say equal, and it's like get that value from that cell. And get that value from that cell. Great. Now, I could type in the negative 0.1, but I could just say equals and click on that cell, and that number is automatically there. This dy dx value is done with cell references. Now, what's interesting here is that if I take this cell and copy it down to the lower cell, it's going to change the cell references so it's pointing to the cells that are 2 and 3 cells over to the left of this cell. So if I simply grab this thing called the fill handle and pull down, it'll automatically adjust the formulas so it's now pointing to the correct values. Same thing is true if I pull down here. You can see again that the cell references have changed to the cells that are 1 and 2 to the left of the current cell. And same thing is true for these two values. And if we checked that 2.81 is the same as we got by hand. Now the real power. Now that I've got the second row all complete, I could just pull down here 3 more times, and there is our estimate at what's going on at 1.5. Okay, all the cell references came down, and that was a relatively easy spreadsheet to make. Now, you're not going to be able to do that on the AP exam, but certainly there's more important, more broader set of topics than what appears on the AP exam. All right, that was a lot of fun.